Now, theorem 10.1, the tangent at any point of a circle. So here is a circle with this with the center O, and I am drawing a tangent at this point, say P. I have drawn this tangent. Okay, so the first part, the tangent at any point of a circle is perpendicular to the radius at the point of contact. So at this point of contact, I am going to draw the radius. This is the radius here. So I write this as radius. So I'll say this is R, this is the radius, and this is the tangent. Here, this is the tangent. Now, is perpendicular. So this angle is always 90. This is what we need to prove. That the angle between the radius, this radius, and the tangent here is always 90. So for that I've taken here that is a circle. Let's get back to our diagram here. Now this is the circle, and to this circle I have drawn a tangent. This is the tangent here. Now I take a point P on the circle, and after I take a point P, and I take another point Q on the tangent. Now this point Q will definitely lie outside the circle. Now why will it lie outside the circle? Because if it were to lie on the circle or in the circle, then that XY would not be a tangent, it would be a secant. Because remember, a tangent, what is the definition of the tangent? Is a line that intersects a circle only at one point, and this tangent XY is intersecting the point, the circle, only at one point, that is P. Fine. So we need to show that this angle is 90. Our question is to show that angle OPQ equal to 90. This is what we need to prove. So now we'll get on to the proof. Now if you see here, we have the radius. This is the radius. OP is a radius. So OP is radius. Now we'll look at OQ. Now OQ is the radius still here, plus there is something more, plus this part. Have you seen this? So if you see as OQ is equal, is definitely is OP plus something more, that little part here. So we know that OQ is definitely greater than OP. We'll take another point, maybe at this here. See another point R. We'll take R. And R again we see what is OR. OR will be radius plus this little bit. So also OR will be greater than OP. You take any point on the tangent and you will find that the distance of the point from the center will be greater than OP. OQ is greater than OP, OR also is greater than OP. So now I can say that OP is the shortest distance from O to the tangent, and the shortest distance is always the perpendicular. So I can say OP is perpendicular to XY. I repeat again that it's a definition that OP, the shortest distance, is always the perpendicular. In the Khan Academy, there is a video showing this proof, so I will not repeat it. It's very clearly given there. So since OP is the shortest, OP is shortest distance, we can say OP is perpendicular to XY because it is shortest. So we prove the tangent at any point of a circle is perpendicular to the radius. So we have proved that this angle is 90 degrees. We go to the next theorem, that's 10.2. It's on page 211. The lengths of a tangent drawn from an external point to the circle are equal. So here is my external point P, and from P I am drawing two tangents. One is PQ, one tangent, and this is PR, the other tangent, and I have to show, that is my question, I have to show that this is equal to this, PQ equal to PR. That is my question. So for that we will complete the triangle. So I join this up, OP, and this is OR, and I will join here. So I have two triangles. So which are the two triangles? One is triangle OPQ, and I have triangle ORP. Let's prove that they are equal, congruent. So I have here a 90 degrees, and this is a 90 degrees by definition. Radius and tangent are perpendicular. This is my radius. Here is my radius here. This is my radius, and this is my tangent, and the angle between them is perpendicular. This is my radius, this is the tangent, and the angle between them is perpendicular, is 90. Now we need another part, and we know that these two also are equal. This is equal to this. Why? Because they are the radius, and this is common here, this is common. So by which theorem? We have the R, right angles, the hypotenuse is common, and the sides are equal. So by RHS the triangles are congruent. So here I write angle OQP equal to angle ORP, which is equal to 90. So we have OQP, the red angles are equal to 90 because the radius and tangent are perpendicular. Then the next part is, we know OQ equal to OR because the radii of the same circle. And the last we have OP equal to OP, which is a hypotenuse, and they are common, it's common side. So triangle OPQ is congruent to triangle OPR by the RHS test. So we can say now, we can say PQ equal to PR, and the reason CPCT. We will be using this property a lot. So if I have a circle, and from a circle if I draw two tangents, they will always be equal. One thing. And the next thing that we use a lot is this. The angle between the radius and tangent is always 90. These two properties will be doing a lot of sums based on them.